You're getting close to beating Sir Roger Penrose's record.
So today, I wanted to present a few case studies, a few examples of discrete symmetry reduction in dynamical systems. These are all examples, okay, of discrete symmetry reductions. So first, I'll talk about some flows. The first one is the Lorenz system. So Lorenz system is famous in chaos as a paradigm of chaos. It's a three-dimensional dynamical system, and it's nonlinear. It was born as a climate model, as an approximation, let's say a toy model to a weather model. So as far as we are concerned, we care about this because it's got this, let's say, this attractor. That is a figure from a chaos book. From some value of the parameters sigma, b, and rho, those are parameters, and the variables are x, y, and z. Instead of some values, we have this two-lobe chaotic attractor. So basically, the dynamics sticks on this on these two lobes, and it's actually chaotic. So there's chaos. But now because here we're focusing today on symmetries. Okay, so one can see, or can at least guess that there's got to be some symmetry here due to the two lobe, but also one can also see it from the dynamical system itself. So one of the things is, as the shape of the attractor suggests, the system is equivariant under the Z2 symmetry. So it's a pi rotation about the Z-axis, right? We got the X, Y, and Z axis, and this rotation is just turns the X and Y into minus X and minus Y. So equivariance means that given symmetry operation G and the solution to the system Ft of X, this is already the solution, right? Given the symmetry operation, you have that Ft of G of X equals G of Ft of X, right? So that does not mean that the system is invariant. It just means that it's equivariant, meaning that it has that kind of symmetry, right? And in this case, the G symmetry is the rotation about the z-axis, right? Now, we can actually see that in the case of Lorenz, the system is indeed this equivariant, because V is the velocity field. The velocity field basically is the right hand side of the differential equations dynamical system. If we apply the G of X, which is in this case is equation 2, that is the rotation, right? Then we just invert the signs of the X and Y variables, right? And then if you notice and compare it with the previous system, right? It was this one before, right? As we saw it at the beginning, right? This one. Then you will see that it's actually just just the velocity field with the minus sign, in front, at least as far as the first two components are concerned, right? The minus the X and the Y components. So then the equivariance, the definition of the equivariance has to do with the solution, right? Not with the velocity field. But the formal solution to the velocity field is actually the integral of it, at least the formal solution, right? So if you show this for the velocity field, then you also get this property 3 that we were actually trying to show. So this Lorenz flow has this symmetry around the z-axis by a pi rotation, right? Now, intuitively, what will happen if you reduce the symmetry, this is another figure from a chaos book, is that you go from a 2-lobe attractor to a 1-lobe attractor. Let's say that you can just reduce the symmetry. And what is it that we're doing? Well, ideally, given a Poincare section parallel to the z-axis, which is basically this plane that you see vertically that intersects the z-axis, then the fundamental domain M would be the half space between the viewer and the section. And then the full flow would be just captured by reinjecting back into the actual fundamental domain every trajectory that exits it. Okay, by just making a rotating about the z-axis. But how to do that in practice? You can do it by hand. There is indeed a symmetry. There's indeed like a coordinate change that that takes us to the fundamental domain. And of course, we in this case, in the case of a Lorenz flow and Lorenz attractor, we can find it. So how to find it? If you write the Lorenz system in cylindrical coordinates, so r, theta, and z, so the coordinates on the plane xy would be the polar coordinates, right? So r would be, x would be r cosine theta, and then y would be just r sine theta, right? And then z is still z because it's cylindrical coordinates. Then if you rewrite the Lorenz system in these coordinates, you realize that every time that the angle appears, well, then the angle is actually doubled. So for the transformed equations for r dot, theta dot, and z dot, everything depends on sine 2 theta and cosine 2 theta, besides r and z. Okay, so then you can guess, okay, because everything depends on r2 or 2 theta and not just theta, and you can say, okay, well, then the rest of the coordinates are r is x squared plus y squared, right? And this is also equal to minus x squared plus minus y squared. And then sine of 2 theta and cosine of 2 theta, you can do the same thing. So you can see that both of them are actually invariant under this pi rotation about the z-axis. So that means that the polar coordinates, so the cylindrical coordinates, make the system actually invariant under the pi rotation, so the Z2 system, the Z2 symmetry. So we can infer that the coordinates act at a Z quotient, the Z2 symmetry out of the Lorenz flow, which means that Ft of r theta and z equals r of Ft of r theta and z. This is actually the same as Ft r theta and z. So it's not only equivariant, but it's also invariant. However, that's not yet the fundamental domain. Okay, so for that, we can guess a set of coordinates that replace theta with 2 theta instead. So r cosine of 2 theta, r sine of 2 theta, and z. And this is how you write these coordinates in Cartesian coordinates, right? And then there's an exercise on the chaos book 11.5, I think, where you can plot this as seen from above, so only the projection to the v and w coordinates, right? The transformed coordinates of x and z, of how the 2-lobe attractor becomes just 1 lobe under this change of coordinates. So this is an example where we have spotted a particular symmetry that was the Z2 symmetry, and then we have also identified a set of coordinates that make the system not only equivariant but also invariant under that symmetry, the application of that symmetry, and finally the change of coordinates that take the system to the phase space, to the fundamental domain. Okay, so this is actually quite a nice example because the system is so important. It is chaotic, and it's actually dealt with rather simply. However, one does not need chaos to reduce symmetries. So let me show you a simpler example instead, which is not on the chaos book, but you can see it and then you can use it as an exercise. So there's this nice system which is a nonlinearly damped oscillator, right? It's got the acceleration and then the speed that makes the damping. Right, and this is like an elastic force that makes it an oscillator, and that we can turn from a second order ODE to a dynamical system that is to two first order ODEs, right? With me is just a parameter, and this is called Van der Pol oscillator. Okay. Some people call it Rayleigh oscillator. It depends on them, but I'll call it Van der Pol oscillator. So now, if you plot it, this system is in 2D, right? And it's a continuous time dynamical system, so there can be no chaos here. Okay, this system can have no chaos, and in particular, the system instead, the dynamics converges to a limit cycle. So this one was an initial condition here at around x equals 2 and y equals 2, right? And this converges rapidly to a limit cycle, which is this one here. And this one has two arms that are like the short arms where the dynamics is slow, and instead the horizontal arms where the dynamics is fast. So again, here there's no chaos, it's just a limit cycle, right? However, here too, you can spot the same symmetry as before. That is, you can verify that the Van der Pol oscillator is Z2 symmetric or again equivariant. So this, sorry, I left the Z here. There should be no Z. It will be just X and Y. Okay, so just a V R of X and Y, and then you just apply. That will be just the minus. You apply the switch. X and Y goes to minus X and minus Y, and then that what you obtain is the velocity is minus the velocity field of X and Y. There should be no Z. It's in 2 dimensions. Again, just like before, if we rewrite the system in polar coordinates, we'll see just like before, it depends on the coordinates. The polar coordinates are r and theta, but again, here you have cosine square of theta, cosine to the 4th power of theta, then sine of 2 theta, and so on. So there's no single sine theta or cosine theta. And on the other hand, both sine square and cosine square, and also cosine of cosine 4th of theta cannot be rewritten in terms of 2 theta, right? Of trig functions of 2 theta. So again, this depends on 2 theta, and we can make the same change of coordinates as for the Lorenz system before. So now one can do it as an exercise if you like it. This is simpler than the Lorenz system because it's 2D, and you can try plot the symmetry reduced Van der Pol limit cycle and see how it looks. Again, you see here you have 2 arms, so maybe it's going to be like it's going to be like you see the symmetry reduced stuff has XY symmetry, so it only has half of it. And this is a simpler system. This is just to show that again, even on simpler systems such as oscillators, you can have symmetries, and it can be useful to reduce them. So this was the first part, and it's mainly about flows. 2 examples of flows where discrete symmetries apply. Now, in what follows, I would be dealing with discrete time dynamical systems such as billiards or some maps too. Now, in that case, it turns out that it's to be also helpful to talk about transfer operators. So somebody raised the issue maybe a couple of weeks ago, I remember, and we were talking about not only like possibility of describing the flow by differential equations, but also by densities of trajectories that move, that are actually transported by the flow. In particular, if you have a flow that is, is a solution of a set of differential equations, let's say x dot equals d of x, then you can write an equation, it's called the real equation, whereas warm, let's say, of trajectories is adapted by the same flow by this equation here. Visualizing it, so you start with the density of trajectories, and then the flow itself just carries them to somewhere else in the phase space altogether. So while the flow again is ruled by the differential equations, and instead the let's say a density or trajectory is instead carried by, and this is actually governed by the reveal differential PDE. Right? Now the formal solution to that, and so you can also write the evolution of trajectories in an alternative way using this linear operator, which is called Perron-Frobenius, and which has this delta kernel. This delta kernel means that exactly that density is actually mapped, enforcing the condition that x be actually a solution of the flow with some, initial condition x naught for all the initial conditions that you want to consider. So all the initial conditions, let's say, of this mi, which is say some density or some support at the beginning, at the let's say at time 0, are then carried by the flow through this evolution operator. This is important because oftentimes you cannot really solve the differential equation. So we will use in what follows in this course some methods aimed at extracting a part of the spectrum of this operator. And this is actually very interesting because it gives very useful information about the let's say the long time dynamics statistically. Now, symmetry conditions also apply to the transfer operator. So if we assume, as before, some kind of equivariance, right? Just like this, so that basically f, which is the solution of our differential equations, is symmetric under the application of some symmetry G, so we can transfer this to the transfer operator. We can apply this to the transfer operator as well. And so we do so by applying the same symmetry to y, which is the variable on the output, okay, and x, which is the variable in the input of the operator. So the operator is actually dual because it's got two variables, right? It's a linear operator, and we apply the symmetry to both. And for now, what we can see is that we've got basically the same the flow that is still constrained to the trajectory, the classical trajectory, to the dynamics y equals f of x. Is this the same thing, or does it mean, how do we actually write the equivariance condition for the transfer operator? Okay, so this is, of course, This is the way I have derived it. I am not entirely sure. We were discussing this with Predrag a few days ago, but I think the concept should be correct. So starting again from the symmetries that are applied to the, let's say, to the variables in the operator, you write the operator, you rewrite it also with the symmetry applied to the variables, and then you make a change of variable, and finally you should get, if the operator is equivariant, right, that basically it's just applying the operator to the row of x. Now, the symmetry condition, in other words, f of x equals g minus 1 f of g of x, should be equivalent to this condition here, where the operator with the variables to which the symmetry has been applied is still the same as before. So of course, you know, this should be the equivalent of the equivariant condition for a transport operator, instead of for the flow that we have seen before. Let's consider an example just to make things a little more down to earth. So consider a Z2 symmetry operation for a 2D map. Let's say such that we just change the x and y into minus x and minus y with this matrix minus 1, 0, 0, minus 1. The phase space can be decomposed into symmetric and anti-symmetric spaces by means of projection operators. Now, this is a standard, let's say, a standard procedure, but it's actually very useful, and the transfer operator can also be split into symmetric and anti-symmetric. Now, you know, intuitively, right? We have a group symmetry group which is C2. C2 is formed by the identity and then this flip condition x y into minus x minus y, right? So any function can be also split between two projectors that represent symmetric and anti-symmetric dynamics, and we can do that also for the operator. Now, of course, minus y means that we are applying the symmetry condition. Sorry, the flip condition. So the C operation to 1. Again, y and x, both y and x are vectors, right, of two variables each, right? So this is the output variable. So this is what we're doing. We're just applying this operation C to the output variable of the operator. Now, this is just an example, but it's it's a general procedure. So and in fact, this is the general formula for a projector, where, let's say, this is also, I took it from this paper that was written by Cvitanovic and Eka, but it's also in the book by Tinkham, for example. I think this is a general procedure for every operator or function, not only for the transport of. What does it mean? The projector is basically a sum of the characters of the irreducible representation, and this is times the symmetry operation. The group characters basically are the traces of let's say this is each this is the matrix of the group element H in an irreducible representation. Now, what matters to us is, at the end of the day, the the transfer operator or the transport operator is split into a sum of reducible space contributions. And this can be beneficial, as we will see later, when we compute the traces of the operator, because the convergence of the traces is actually sped up this kind of decomposition. In the example, the Z2 groups are two irreducible representations, and such that their characters are one for the identity, one for C, and the other one is one for the identity and -1 for the C operation, so for the flip, right? And that's exactly what yields in this sum here these two symmetric and anti-symmetric projectors. Now, the eigenvalues of the transfer operators are evaluated by means of traces. So also in the fundamental domain, if we care about the spectrum of this operator here, then at some point we will compute its trace, and this can be also done using this decomposition. And contributions to the trace come from periodic orbits, and that's why we care about periodic orbits. Okay, so again, this is not the only possible approach, but it's the reason why then we study periodic orbits. It's because we want to extract information on the spectrum of the evolution operator, and so that comes from the trace, and you can see from the formula of the trace that the contributions are picked up by the paths that start and end in the same place. Those are the periodic orbits. Okay, so I switched to the transfer operator decomposition, or the transport operator decomposition, because there are systems such as the billiards, which is what I'm going to talk about next, where you cannot just run a long trajectory and take an average, as some people do with, for example, attractors. So repeller, like this one, a 3D scatter that we have briefly seen last week too, is a system where everything escapes eventually, right? So if you want to understand something about the chaotic dynamics, the transient chaotic dynamics, then one way is to look for the unstable periodic orbits. So that's why then we care about this stuff. So the 3D scatter is another paradigmatic example system that we see in the chaos book. And so this one is formed by 3 scatterers, right? And they are located at the vertices of an equilateral triangle, right? And the symmetry group in this case is the dihedral group. So dihedral group means that it's got let's say six elements. One is the identity, and R and R2 are rotations, about the rotations of 2 pi over 3 and 4 pi over 3, or 2 pi over 3 and minus 2 pi over 3, depending on how you see it. And then we've got 3 flips, so around the axis. The axis of symmetry are the ones that join the center of every scatter with the center of the system, right? So 1, 2, and 3, right? This one, S in particular, is the simplest one, is the flip around the x-axis, right? Okay. So it's nice that we can see the operations as 2x2 matrices in this case. So some group properties, some properties of the dihedral group. So dihedral group is not abelian. So it means that it's not commutative. So for example, if you apply the flip, around two different axes. For example, this S and S1. So first round is first S1 and then S. And this one is a rotation, let's say, of 2 pi over 3. But if you do the inverse and you switch them around, then you will get the rotation in the opposite sense, right? And this one can also be seen by multiplication table, which you can also find in the chaos book, or also in the book by Tinkham is available. And the multiplication is just, like what happens if I compose, let's say, two operations, and then in the middle I find the operation that I get. If I do so, D3 has 6 subgroups: E, ENS, then ENS1, ENS2, ER, and R2. So basically, the identity alone, and then the identity accompanied by, in turn, all the flips, and every one of the flips, and then the two rotations together. So subgroup has to be closed, must satisfy closure, right? So if you add two elements of a subgroup, you have to have still an element of a subgroup. That's a requirement for a subgroup, and there are 6 of them in D3. And then besides that, there are 3 classes. Three classes. So 3 classes. The definition of classes, I think we have seen last time. It's basically about operations or elements that are conjugated to one another through the application of another element. And so we have E, S, S1, S2, and then R, R2. So there are three classes in the dihedral group. Now these are just a few properties of the dihedral group. Again, I think they can be found either in Chaos book or even Tinkham's book. I found them. Now, so the pinball is an open system, so everything escapes eventually. So the transient chaotic dynamics is nailed by the trapped orbits. So that's the reason why we care about the periodic orbits. It's because if we want to get information about, for example, the escape rate or other stuff concerning the let's say long time, in this case, again, the system is open, but it says statistical information on the dynamics. We need to, well, we can definitely use the unstable periodic orbits. And those also can be reduced using the symmetries. While before we have reduced the whole attractor, because we had differential equations in the case of flow. Now, in the case of maps, or in this case of billiards, we do have a whole the real space, which we can reduce to a fundamental domain. Then we can see how the orbits can also be reduced, and with them also the so-called symbolic dynamics. Symbolic dynamics is basically a sequence of symbols that we associate to each let's say trajectory, depending on where it goes. So in this case, for example, depending on the sequence of disks are that basically our particle hits before escaping, we can basically make a symbolic sequence, and by doing so we can also label the periodic orbits. So here there are some examples of these orbits that just bounce back and forth, the 2, 3, because it bounces back and forth between disk 2 and disk 3, and so does 1, 2, and so does 1, 3. And then there's this other one that just bounces from 2 to 3, from 3 to 1, and from 1 to 2 in a triangle. This one that you see on the right is an orbit of period 4, because it goes, let's say, from 3 depending from 1 to from 3 to 2, from 2 to 1, then back to 2, and then back to 3, and then it closes here when it comes back. So it's an orbit. It's a sequence. It's a periodic sequence of 4 symbols. So the symmetry operations can also be applied directly to symbols, right? Because, for example, if R is a rotation by 2 pi over 3, right? For example, if I apply it to this 1, 2, just this bouncing orbit here, then what do I get? Well, I can get maybe the same orbit here, which is 2, 3. All I've done is just a rotation, and in turn, if I apply the same rotation to the 3, I will get 1, 2. Sorry, 3, 1, which is the same as 1, 3, because again, this is a periodic orbit. The overbar here, the overline, implies a periodicity, right? Let's go to 2, 3, 2, 3, 2, 3. It's bouncing back and forth. So now, of course, we can do that with a lot of different orbits, right? So I just showed you a period 2 orbit, but now we can also do this with a period 3, and also using a different operation. So this one is a flip. That's a flip around one of the symmetry axes that we apply to this orbit 1, 2, 3, right? And effectively, what it does, well, basically what it does is just to switch 2 and 3, right? So, and it's the same as going backward, or equivalently again. It's the same thing that you would obtain by switching this 2 and this 3. But also 1, 2, 3, and 1, 3, 2 form a group when invariant cycles under C3, under rotations, basically, and this is something that can be easily verified. If we come back to the orbit that we saw before, that was the period 4 orbit that goes back and forth between 2, 1, and 3. This 2 can be, to this 2, we can also apply symmetry operations such as S1, let's flip, and we discover that this one is instead is invariant. So again, what we're doing here is, like, you see, I'm starting 1, 2, 1, 3, which is this one, right? So it's going like this. It's going first to 2, then back to 1, then to 3, and then back to 1, and that's where it closes, right? So if again I'm flipping it around one of the symmetry axis, and then I get 1, 2, 3, 2, okay, and one can do the same. This one is what is instead applying a rotation 1, 2, 1, 3 again by 2 pi over 3, and I get 1, 2, 3, 2, which is basically the figure, 1, 2, 1, 3. Then I apply the rotation. This is by 2 pi over 3 counterclockwise, right? And again, I do it again, and then I get 1, 3, 2, 3. So there's all this bunch of orbits which are basically they're the same under rotations or under flips. So if we were to reduce to the fundamental domain, we would always have only one left out of all these. This is another example, a 6-degenerate 5 cycle. So basically, again, there are 6 like this under this is a flip around the x-axis, okay, and then I get this one, which is 1. Now, besides the 3 symmetries, pinball has time reversal because it's a Hamiltonian system. So for every orbit, it's time reversal. So basically, I take the sequence and then I reverse it completely, right? Then this is also true. Now, of course, if you reverse it from here, you get 3, 1, 3, 2, 1, 2, 1, 2, 1, right? But again, this is cyclic, right? Because it's a periodic orbit. So you can also write it in this way: 1, 2, 1, 2, 1, 2, and 3, 2, 3. So this has to be always kept in mind for the for Hamiltonian systems that often have, like in this case, time reversal symmetry. So now, how do we reduce to fundamental domain in this case? Well, one possible way is, first of all, to reduce to symbolic dynamics. So we switch from 1, 2, 3 symbols for each, let's say, bounce, to instead take 2 bounces and see whether the second bounce goes back to where it started or where it goes to a third disk. So if it goes back, then we say that this is 0. And if it instead goes to a third disk, we call it a 1. Together with the symmetries that we've seen before, can reduce the whole available space to a fundamental domain, which is this light yellow area here. And this light yellow area here is basically given by, let's say, 1/2 circle of the disk. Actually, it's a quarter, and its intersection with the symmetry axis. So now, for example, the orbit that was 2, 3, that was this one that is bouncing back and forth between 2 and 3. This is always going back to the disk it hit before, right? So it's basically a sequence of zeros. So this one that was an orbit of period 2 in the new fundamental domain becomes an orbit of period 1. Same thing with this orbit, which is triangular here, 1, 2, 3, because this one is always going to a third disk. It's never coming back. So it's like writing an orbit of 1, 1, a sequence of ones in the new symbolic dynamics. This orbit here that went from 1, 2, 3, 2, and so on. This is always going to back at the first bounce, and then second. Sorry. And then it's actually hitting the third disk before going back to the disk it came from before. In other words, in the new symbolic dynamics, this is 0, 1, 0, 1, so it's an orbit of period 2 instead. So we went from period 4 to period 2 in the fundamental domain. So this is basically what it would look like in the fundamental domain. This is the period. This is the 2, 3 that becomes 0. This is the 1, 2, 3 that becomes 1. This one, and then I believe that this one instead is this one instead is the 1, 2, 3 that becomes 0, 1. This is another example of a 9 cycle, which this one that instead, when you reduce it, just becomes a 3 cycle in the fundamental domain. So this is an example how the 3-disk scatter can be reduced by using the symmetries. So another system that we're familiar with and was introduced when we talked about billiards is the Bunimovich stadium. So the Bunimovich stadium has the stadium shape, and it's got 2 axes of symmetries, right? The X and the Y. And then it's got an additional symmetry, which is the C2 symmetry, that is the X, Y, and 2 minus X minus Y. So this mirror symmetry around the origin. So the symmetry group is C2V, which is formed by the identity, then SX, SY, so these are flips around the X-axis, the Y-axis, and then the C2, which is again this mirror with respect to the origin, right? So now this one in black I took is an example of an orbit, right? So this would follow in the full size system, right? It would actually go through and bounce. And instead, if we want to reduce it to the fundamental domain, which now is the quarter billiard, so just a quarter of this, right? What we do is we turn the X, the positive X-axis and the positive Y-axis, and also the origin into some kind of mirrors, right? So instead of continuing, for example, this orbit from the upper half to the lower half, we just bounce it, and we do the same thing. Then when it reaches the origin, we just go back. Or instead, in real space, this would just continue, right? Again, this SX, SY flips around the X, Y axis and a rotation by pi. These are the symmetries of the Bunimovich stadium. Now, again, here we also care about periodic orbits, right? So again, this we may also care about here. We may also care about periodic orbits, and here are some examples of periodic orbits in the full billiard on the left, and instead reduced in the quarter billiard. Right, so on the left you have like this orbits which are the shape of a rhomb, right? So it's going from the let's say from the from the tip of the cap of the billiard right here, and then this is the only segment in the fundamental domain. So everything should be a reflection. So again, when we reduce the symmetry, the orbit to the, let's say to the fundamental domain, this is just going back and forth here. This is another orbit, this one, and this is again orbit that goes back and forth. So it goes like from the bottom to the top, then to the bottom left corner and back to the top. So it's an orbit of period 4, 1, 2, 3, and 4. And again, this one can also be reduced. Now, of course, you have to imagine, you know, the y-axis is here, so the first segment you have to map like a mirror to the top of the to the first quadrant, right? And then it's like as if again you had a mirrored orbit, and this is on the right is the reduced one. So again, this is another thing that we can do, and these are some other examples. Notably, let's say this one in the left in the top left corner. This one looks like a triangle. Now, in reality, this is in the full space. This is a bow tie orbit, so it makes a bow tie. It just goes like this, and then it's just reduced to a triangle. This one on the bottom right is a rectangular orbit, right? So it just makes a rectangle in the stadium, and again, this one we have reduced to a rectangular to just like this simpler orbit in the fundamental domain. So this is another example with a different system. Now, again, here too, one can proceed and try symbolic dynamics. So there are some papers here by Kai Hansen and Predrag from a while ago, and from these two people who did it, who actually started a symbolic dynamics for the Bunimovich stadium. Now, this is a little more complicated than it looks, because one can associate like let's say 4 symbols, let's say 1 per each segment, so right cap, left cap, and then top and bottom straight segment. But it turns out that one should introduce symbols that are different depending on whether the trajectory is bouncing off, let's say clockwise or counterclockwise. So this is a little bit, because otherwise there would be some ambiguities in describing the orbits symbolically. This is just to let you know. Of course, this is not trivial. There have been works and papers written on this. Interestingly enough, this is a different symbolic dynamics. So symbolic dynamics is not unique. You can make the symbolic dynamics that you want. Okay, so this was made by Kai Hansen and Predrag, and this is slightly different. So in this case, basically the symbol 0 is associated to an orbit every time it hits the cap for the first time. after having bounced off one of the other segments, and then one, if it keeps going, let's say clockwise, right? So here and here it's got 0 and then a 1, or 2 if then it goes like sorry, this is yes, or 2 if it keeps going, like let's say instead counterclockwise. So the interesting thing is that using the symbolic dynamics, one can make a Markov graph. So the Markov graph, what does it do? It tells us where the dynamics can maps from where. So if you partition, let's say in this case, this is just the real space, but this is usually done with the phase space, and then you can turn the symbols into nodes, which is what has been done here, and then you have a graph. And a graph is telling you each, let's say, symbol where it can map. It can map into which other symbols. So, for example, when you have this 0 that maps into itself, this corresponds to an orbit that bounces back and forth between the two outermost points in both caps. So this is a periodic orbit which is unstable, right? But it oscillates from left to right. Instead, going from period from 3 to 4 and back to 3, that means these are like the so-called bouncing ball orbits. They're bouncing off the segments, like let's say the lower and the upper segments of the straight part. So one can, this is very useful, and we will see later it proves useful also when you want to compute the spectrum of the transport operator. Now this is also done with the symmetry reduced symbolic dynamics. This was done by Kai Hansen and Predag. And this is a bit counterintuitive because what they did was to introduce a lot more symbols. I think these are 11 symbols, but it turns out that the Markov graph is simpler, and there are convergence advantages for the spectrum or for the trace of the evolution operator. Of course, this is just to give you an idea, but we will not get into this. Also, it's a bit of an anticipation from what will come next in the course. So because this was only about symmetries, then I will not go any further, and I will instead briefly talk about one last example of a system, which is coupled map lattices, where we also encounter symmetries. So coupled map lattices are dynamical systems with discrete space and time and a continuous state variable, like a field. That would be this phi. Right? So again, we have two indices because the index, so the subindex n, the index for the time evolution, whereas instead the I is for the lattice site because we have plenty of lattice sites, right? So then F is the dynamics on one lattice site, which is comparable to our the solution of the differential equations. Of course, this though again is discrete space and time, so it's like a map, right? And this one is coupled to and instead there's another function that couples nearby lattice sites, right? So this is a model. This is a kind of model that is widely used, let's say nowadays, also to describe spatial-temporal chaos in general. So it can be, I've seen it to describe turbulence, or to describe also biology, many things, engineering, and so on. Now, this can be equivalently written as a system of n coupled maps, deciding how many sites you want your lattice of. So for example, in the simple case of n equals 2, and also choose g equals to f, we have these coupled maps. Okay, this is a very simple form. It's also kind of symmetric. So if you have a equals 0, then you have uncoupled dynamics. So it means that on every lattice site, every lattice site follows its own independent dynamics given by F, and there's no interaction between nearby lattice sites. Right? Now, suppose that F is chaotic. So, for example, if you have Bernoulli shifts is this maps where you basically, or which is conjugated to the 10th map. So you have a symbolic dynamics and two symbol dynamics, and you have fully developed chaos. And we're interested in the periodic orbits and the periodic points, for example, period 2. So then the single map has, let's say, these 4, 0, 0, then 0, 1, 1, 0, and 1, 1. You can verify also from here, right? So there are two that are period 1, but period 2 is period 1 repeated, so it's okay. And 2 that are 0, 1, and 1, 0. This is the single map. Then how do you get instead the ones from the couple? Well, again, this is a simple case in which you only have two sites. So the two-dimensional map has for the 2 equals 16 periodic points, and these are classified as 6 prime orbits. So prime orbits means they cannot be reduced to orbits, to simpler orbits. So remember here, if you go vertically, that's the temporal dynamics. And if you go like horizontally, instead that's the space. So x, y, and so 0, 0, 0, 1, 0, 0, 1, 1, 1, 0, 1, 1, and so on. These are orbits that cannot be reduced to a lower period. Then we can do their cyclic permutations. So we permute them vertically, right? So from 0, 0, 0, 1 becomes 0, 1, 0, 0, and so forth. And then we have 4 period 1 repeated orbits, which are the repeated ones. And the total is 4 to the 2, right, which is 16, because we have 4 initially in the uncoupled dynamics, and then we have to match them. Right? Now, here we haven't done any symmetry reduction operation yet. However, symmetrically coupled lattice of n spatial sites has symmetry group Tn of order 2n. So we have spatial cyclic permutation plus reflection. Of course, if n equals 2, the cyclic shift is the same as the reflection. So d2 equals c2. So we only have this group of identity and s flip when we flip x with y. So the prime orbits of period MP in the fundamental domain can be classified as 2 asymmetric orbits of period 2 in the original dynamics, these two, and 1 boundary orbit, which means x equals y, you see it's 0, 0, and 1, 1, period 2. And then 3 symmetric orbits of original period 4, which, however, we can reduce. So how do we reduce them? By applying the flip xy to yx. The orbits of the last group are all copies of the orbits of the first group, or repeated orbits, and we're left with only these 3 orbits. So that's why reducing to the fundamental domain, then is advantageous, because we're left with, let's say, fewer orbits, and somehow they should be more meaningful, and that will translate into accelerating the convergence of the zeta function, which is what we use to determine the spectrum of the evolution, or the evolution operator. But this was just a simple example, so you can study it a little bit by yourself, and perhaps you can also try as an exercise to desymmetrize the period 2 orbits for lattices with n equals 3. So we go from this C2 to D3 symmetry group. It's a little more involved, but it's also more interesting.